This video looks at prediction with transfer function models. So previous videos introduced the main concepts underpinning predictive control, and they also argued that linear discrete models are a logical basis for any predictions, certainly where they're good enough. What we want to do next then is look at how exactly predictions can be formed, and here we're looking at what happens when the model you're given is a transfer function form. Now, the initial focus will be on CISO systems, because if you're using transfer functions, the algebra for multi-input, multi-output is rather messy, and you'd want to avoid it if you really could. We're also not going to include dimensions except where we really have to make things clear. Usually they're pretty clear from the context. The Creamer model then. This is the most common transfer function model used in MPC. Within its structure, it will actually contain many other transfer function forms, so that's a good point. But the key reason it's used is because the uncertainty is included in a way that gives us a good representation of slowly varying disturbances, which is realistic in many of the scenarios where predictive control has been used. So here's the Creamer model then. You'll see we have AY equals BU plus T zeta over delta. And the key thing here is this extra term on the right. Zeta is a zero mean random variable, so zeta over delta represents slowly varying disturbances, and in particular the T of Z is considered as a design parameter. Now you could identify T of Z from a formal identification procedure, but what people find is it's better to treat it as a degree of freedom because it affects the control design. The basic concepts of prediction then. Now, discrete models are usually written implicitly as one step ahead prediction models. So that means if you've got data from sample K, you can use your transfer function model to determine the data at sample K plus 1. So we'll illustrate that. Here's a simple transfer function model. A of zy equals B of zu plus dk. If I expand out A of z in terms of z inverse, as I've done here, and expand out B of z, and then I write it in the more normal one step ahead prediction form like I have here, then what do you notice? You get yk plus 1 plus a1yk plus all the way down to anyk minus n plus 1 equals b1uk plus b2uk minus 1, and so on. And the key thing here, if I use a red bracket, is everything in red is known, and therefore you can get yk plus 1 in terms of all the other things in this equation. So you can consider it as a one step ahead prediction model. So there you see I've rearranged it there, moved everything that was in red brackets to the other side, so I can form yk plus 1 based upon all the other data. Now, you'll notice that we've not used the double notation form that was described in the previous video, because largely it's going to be pretty obvious when we're talking about prediction, so we'll keep the notation as simple as possible. What's the significance of the Creamer model then? The reason we're using the Creamer model is because the way it incorporates the disturbance estimate means we can get unbiased predictions in the steady state, and that's also irrespective of parameter uncertainty. So how do we do this? Well, here's the original Creamer model. AY equals BU plus T zeta over delta, and what we do is we multiply the whole way through by this delta operator. So you see we get A delta times Y, B delta times U, and T times zeta. Now, the advantage of this is because zeta is a zero mean random variable, then this term over here is going to be a zero mean random variable, and ultimately we're therefore going to be able to ignore it. Okay, so this incremental form basically means that we can get unbiased predictions in the steady state. But what it means is we're basing our predictions on increments. You can see here I've got delta y and delta u as opposed to absolute values. So for convenience, the output is often measured as its own value, not as an increment. And so what we tend to do, and this is a bit of trickery, but it's just how conventions have come out, we use the output, the actual output, not the incremental output, in our model, but we use the input increment. It just makes the algebra easier, so I wouldn't try and analyze it in too much detail, just accept that this is what people do. So what we've got, if this was our model based upon the incremental variables, a delta y equals b delta u plus t zeta, what people do is they write it like this. They group the delta with the a on the left hand side, so I have a delta all times y, but they group the delta with the u on the right hand side, and you'll notice we're assuming zero mean for the zeta, so that disappears. So we combine the a with the delta, but we then combine the delta with the u. And what this does is it just gives us a convenient way. Y, we get absolute measurements, but delta u, what we're saying is how much do we want to change the input, and we're not too worried about the current underlying value. Let's get on with prediction then. So discrete models are one step ahead prediction models. That is, given data at sample k, we can determine data at sample k plus 1. Here's the model that we're trying to use. Capital A y equals b delta u, where capital A is defined as little a times delta, so we combine the delta with the a. The b is unchanged because we've got delta u. Let's expand those out in terms of powers of z inverse, which I've done there, and then if I write down my difference equation model, you'll see you get this. Yk plus 1 plus capital A1 yk all the way down to capital AN yk minus n plus 1 equals b1 delta u plus b2 delta uk minus 1, and so on. Okay, and the key thing here is you'll notice there's no need for a disturbance estimate in this prediction because it's implicit in the fact that you've used incremental variables. So if we assume that the disturbance is not time varying, once we've gone to incremental model, the disturbance disappears. Let's look then at how we might form predictions, not just one step ahead, but many steps ahead. And this is just like the state space video. What we're going to recommend is you can use the one step ahead prediction model recursively to find an n step ahead prediction model. And that's historically how people did it, using Diophantine identities and the like. We've written down then the one step ahead prediction model at sample, or to get the yk plus 1 basically, and what we're going to do is simply write the same model down at the next sample instant. There it is, yk plus 2 plus a1 yk plus 1 and so on, and the next sample instant yk plus 3 plus a1 yk plus 2, and the next sample instant, and so on. So all you're doing is writing down the one step ahead prediction model at each different sample. We've got sample k plus 1, sample k plus 2, sample k plus 3, and so on. Now, what you could do is you could take the value of yk plus 1 and put it in here, and you could take the value of yk plus 2 and put it in here, and take the value of yk plus 3 and put it in here, and so on. However, what I'm going to say to you is I would not recommend this. You can do this, and this sort of is what's implicit in Diophantine approaches, but what you'll notice, and I've written it down here, it's rather tedious, and better methods do exist, and much cleaner methods, so you can avoid lots of unnecessary algebra and keep life simple. So how are we going to do it then? What I'm going to do is go back to the entire set of one step ahead prediction equations. We haven't done anything different there, but we're going to say these can be considered as a set of simultaneous equations, where the unknowns are the future outputs. There we go, I've just written the equations down again, and what do you notice? Here, for example, I've got 4 equations, and how many unknowns have I got? I've got 4 unknowns. Okay, 4 equations, 4 unknowns, linear simultaneous equations, so I should be able to solve these in a straightforward manner, and really the only question is how do I do it to keep my life neat and tidy. So here's the example. We've got 4 unknowns, 4 equations, and you're reminded that all these future u's are not unknowns, they're decision variables, they're things that you are going to choose. How do we solve these simultaneous equations then? What I'm going to recommend is you next put all the equations in a matrix vector format, because after you've done that, the solution becomes obvious and very, very easy to code. Let's start by looking at the left-hand side, which just had the output parts. So I've got yk plus 1 plus a1yk all the way down to anyk minus 1, yk plus 2 plus a1yk plus 1, and so on there. And what I'm going to do is say, if I separate this between the parameters, that's all these a terms, okay, and then the data, then I can actually express it in this form here. And if you're saying, well, okay, what's in this CA, what's in this HA, you can see CA is given by this matrix down here. The top row is just 1, the second row is A1 and 1, the third row A2, A1 and 1, and you'll notice it's got a very nice diagonal or triangular type structure. So you can write down this CA by inspection. Hopefully you can prove that very easily by yourself by just looking at these equations here and seeing what happens if I try to write them as some matrix times the future outputs. In a similar way, if you look at how the past outputs come into the equation, so there's the past outputs yk minus 1 down to yk minus n plus 1, you'll see the matrix that you're multiplying by is this one here, HA. And again, you'll see it's got a nice structure, a nice sort of diagonal type structure. So you can write down these two matrices by inspection for any dimension you like. Here we've got a dimension of 4. In a similar way, if you look at the right hand side where we had all the b coefficients times the delta u's, you can express it like this: CB times the future delta u's, HB times the past delta u's. And again, you'll see this CB has got this nice diagonal structure, and HB has got a nice diagonal structure. So you can write down these matrices by inspection, or you can write a piece of code to create them in literally 1 or 2 lines. Next then, let's combine all of this together. Oh, there's just a warning there. For convenience, when we write CB, you'll notice we start with B1 in the top corner. We ignore the fact that B0 is 0. We basically put it into the algebra to make life easier. So let's combine these two slides, and this is what we get. CA times the future y's plus HA times the past y's equals CB times the future delta u's plus HB times the past delta u's. Now what I can do, using the notation we've had before, I can write that as y future k plus 1. The next vector has actually got past y's, so what we do is introduce an arrow going to the left to say we're going backwards, so I'll call that y left arrow k. We've got the future values of delta u, and we've got the past values of delta u. So basically I can put a shorthand notation for the outputs and the inputs, and once I've done that, this is my overall expression, a very compact expression: CA times the output predictions plus HA times the past outputs equals CB times the future delta u's plus HB times the past delta u's. So finally now, I want to solve for the output predictions. Now that we've got all the predictions in a compact matrix vector format, we can easily rearrange this to find the dependence of the output predictions upon the past or known data and the decision variables. So there's the equation we've got, and you can see we can easily multiply through by CA inverse, which is what I've done here, and you'll see here's my output predictions on their own. They have some dependence on the future input increments, they have some dependence on the past input increments, and they have some dependence on the past outputs. So it's very, very clean. We can see, you know, how are the future variables, the things we want to choose, how does that affect our predictions, and how does the past affect our predictions. Very clean, very easy format. So in summary, it's common to use discrete models for prediction, and this video has shown how if you have Karima models, you can form n-step ahead predictions, and you can pretty much write down what these are without any calculation at all. It's shown how the predictions can be separated into known parts and unknown parts, so we've done that, and the predictions are grouped in vector format for convenience of handling hereafter. Now, we did not consider multivariable transfer functions, but actually if you write your multivariable transfer functions in these difference equation forms, what you'll find is you can use identical conceptual steps, and you can indeed write down the predictions by inspection.